Hello, my name is Ken Chan, and welcome to this presentation which will discuss the concepts of signal-to-noise ratio and noise spectral density in high-speed data converters. The first part of the presentation will go over the concept of signal-to-noise ratio, or SNR, by defining the meaning of SNR. A more detailed examination of the different components that make up the noise portion of SNR will be explored. This includes thermal noise, quantization noise, and jitter of the quantization clock. An example of a calculation of SNR that is dominated by jitter will be provided. The second part of the presentation will examine the concept of noise spectral density, or NSD, and describe how this is different from SNR. Finally, a design example will be presented which will highlight how NSD can be used to estimate the performance of the output of a DAC as it pertains to noise floor-related performance specifications. In real systems, signals are generally corrupted by noise, which results in a noisy signal. Simply stated, the signal-to-noise ratio, or SNR, is the signal power compared to the noise power in a given signal bandwidth. Typically, this is calculated by performing a fast Fourier transform, or FFT, and looking at the fundamental signal power and noise floor power in the frequency domain. The noise floor power is typically the integration of all of the noise within a given frequency bandwidth, excluding the fundamental signal and the harmonics of the fundamental. SNR is then simply the difference between the signal power and the integrated noise floor power. Since SNR is the difference between the signal power and the noise power, there are only two ways to increase the SNR. First, the signal power may be increased to a maximum of the full-scale range. Increasing the input signal strength above the full-scale range is not recommended and will adversely affect the performance of the ADC. The second way to increase SNR is to decrease the noise power. Noise power is typically a result of a combination of quantization noise, noise caused by clock jitter, and noise caused by the ADC aperture jitter and circuit thermal noise. Reducing one or all of these noise sources may help to increase the SNR performance. Assuming that the signal power is kept constant at a fixed level, the SNR can be estimated by looking at the noise power contribution from each of the noise sources. Each of the noise power sources can be treated independently. The three different noise power sources are quantization noise, clock jitter noise, and thermal and transistor noise. Design choices such as ADC selection will include n bits of quantization noise, ADC aperture jitter, and the thermal noise of the ADC design. Sampling clock choice will result in clock jitter noise, and the choice of the sampling rate of the ADC will generally dictate the bandwidth over which the noise is integrated. In general, this is usually the first Nyquist up to Fs/2. The quantization error can be calculated based on the theoretical quantization error assuming a sine wave input. This is given by 6.02 dB per bit plus 1.76 dB. This determines the maximum possible SNR for n number of bits. In a real ADC, there are other limiting factors such as sampling clock jitter, ADC aperture jitter, thermal noise, other system noise sources, the oversampling rate of the converter, and the application channel bandwidth. There are generally three sources of circuit noise: shot noise, flicker, and thermal noise. Shot noise is caused by the p-n junction's DC bias current and is not constant. It generally has a white noise spectral profile. Flicker noise is caused by active circuits and electron carrier movements and generally has a 1/F shape near DC. Thermal noise is caused by the thermal excitation of the resistors and generally has a white noise distribution. Noise in an ADC is dominated by the track and hold circuit thermal noise contribution from the input resistor. Limiting the noise bandwidth to the RC bandwidth, the resulting thermal noise power is given by kT/C. Clock jitter is defined as the random variation of the clock edge compared to its ideal point in time. Variations in this edge will cause the converter to sample the data at non-ideal points in time, resulting in an error which will contribute to the overall noise and impact SNR. The theoretical limit of SNR due to jitter is defined as the minus 20 log 2 pi Fn times total jitter. Total jitter is the combined jitter from the clock source and the additional jitter caused by the internal ADC clock circuits, also referred to as aperture jitter. Clock jitter will cause incorrect samples of the input waveform and will be more prevalent with higher input frequencies. The SNR impact from jitter can be plotted alongside the SNR impact from the thermal noise. At the lower input frequencies, the thermal noise is dominant, while at the higher input frequencies, the noise caused by the jitter dominates. The resulting SNR can be thought of as the sum of the SNR impairments from jitter and thermal noise. The plot on the right can be used to illustrate the greater impact that jitter has on higher frequency input signals. It is quite obvious that with lower frequency inputs, the possible error is much smaller than with higher input frequencies. As mentioned earlier, the total jitter is a combination of the sampling clock jitter and the aperture jitter. The clock jitter is the contribution from the external sampling clock source and can be measured on a phase noise analyzer. The aperture jitter is internal to the ADC clock circuits and cannot be measured by a phase noise analyzer. This is usually characterized by using very clean clocks and high input frequencies to make an estimate of the total jitter based on the measured SNR. Then using the measured external sampling clock phase noise, an estimate of the internal aperture jitter can be derived. This is an example phase noise plot measured on a phase noise analyzer of a sampling clock running at 122.88 MHz. The jitter is the integration of the phase noise from 10 kHz to 10 MHz. In this case, the resulting jitter is 299 femtoseconds. A simple estimation can also be done for the jitter of a clock source if the phase noise plot is available. In the previous example, the integrated phase noise between 10 kHz and 10 MHz is given as minus 75.72 dBc per Hz. With f clock equal to 122.88 MHz, the equation yields a jitter of 299.77 femtoseconds. Some considerations also need to be made for the traditional calculation of SNR based on the jitter and the input signal frequency. Previously, the theoretical limit of SNR due to jitter was defined as a function of the total jitter and the input frequency. However, this implies that the SNR would be the same for an input frequency regardless of the sampling rate. Then the question would be, what advantage would oversampling have? Why not use undersampling for every application? It turns out that the SNR calculation has some dependence on the sampling clock frequency as well as the input frequency. By substituting the sampling clock jitter equation into the SNR equation, the result is two terms. One is based on the integrated phase noise, and the second is a term based on the oversampling of the input frequency by the sampling frequency. This correction term allows SNR to be improved if oversampling is used. This is the more general equation for ADC SNR. This general equation is important because it gives a better estimate of the SNR performance of the ADC as compared to the traditional equation, which uses a simplified estimation of the impact of jitter on the SNR regardless of the sampling frequency or the input signal frequency. In most cases, the ADC clock is well filtered and will have better noise at larger frequency offsets. In some cases, the system requirements are often limited to a specific bandwidth, where you only care about the noise floor performance in a specific band. Using the traditional estimate for SNR would require a much more stringent noise spec and may not be achievable or make the solution more complex and more expensive than it needs to be. Looking at the SNR performance at a specific frequency and over a specific bandwidth allows a more optimized system solution. A simple experiment was performed to validate the general ADC SNR equation. A high-speed DAC was used to generate a clock with a known exaggerated level of noise around the clock frequency. This was used to drive the ADC sampling clock, and two different input signals were sent into the ADC. One tone was at 10 MHz and the other was at 100 MHz. The resulting signals captured by the ADC are overlaid and shown together. As expected, the sampling clock phase noise is coupled onto the input signals at 10 MHz and 100 MHz. The oversampling correction factor improves the phase noise at 10 MHz by the oversampling ratio of 25 times resulting in a 28 dB reduction in noise power. Also at 100 MHz, the oversampling is 2.5 times, resulting in a reduction in noise power of 8 dB. The next section will discuss the concept of noise floor in the DAC output. Here, noise spectral density, or NSD, is the preferred specification versus SNR. The estimate of the SNR for DACs is the same as for ADCs. Similarly, the noise floor is made up of contributions from quantization, clock and aperture jitter, and thermal and transistor noise. The jitter limit for SNR is also treated the same way. For DACs, the NSD specification is generally more important than SNR. The shape of the NSD around the carrier must generally meet some transmission mask. Usually when SNR is required, the system will often limit the bandwidth of the signal with a bandpass or low-pass filter. The noise floor can then be estimated within the passband of the filter using the NSD. This is one of the main reasons most new datasheets are reporting NSD, bandwidth limited, versus SNR, first Nyquist. In real systems, there is usually some tight filter around a band of interest, and all of the spectrum outside this band is filtered out. Instead of reporting the noise floor for the entire first Nyquist, it is more convenient to show the noise power per hertz, and then estimate the noise floor within the passband frequencies of the filter. Let's consider a simple example where a DAC 3484 is running at 1.2288 gigasamples per second and is generating a frequency of interest within the first 100 MHz. Let's assume the NSD for the DAC 3484 is at minus 160 dBc per hertz. If a low-pass filter with a frequency corner around fs/2 or first Nyquist is used and the noise floor is calculated for the entire first Nyquist, the resulting noise floor is minus 72.12 dBFS. However, if a low-pass filter is used with a corner frequency around 100 MHz, then the noise floor within 100 MHz is minus 80 dBFS. By looking at the relevant noise floor only, the specification is better by approximately 8 dB. The SNR of a DAC can be converted from the NSD specification. The NSD specification is the power of the 1 Hz spin. To convert this to SNR over a certain bandwidth, you can simply multiply this by the Hertz bandwidth. For the case of the typical SNR, which is specified over Nyquist or fs/2, you would calculate the noise floor based on the NSD, then adding 10 log fs/2. This noise floor can then be subtracted from the fundamental signal power to give the SNR. For our real case of the DAC 3484, the NSD is specified approximately minus 160 dBc per hertz. If the DAC was sampling at 1.25 gigasamples per second, then the noise floor is then calculated as minus 60 dBc per hertz plus 10 log 1.25 gig divided by 2, or minus 160 dBc plus 88 dB, resulting in an SNR of 72 dBFS. In summary, the noise floor of ADCs and DACs can be specified in terms of SNR and NSD. Depending on the application, it may be better to use one or the other. It is best to keep in mind some of the important points about NSD and SNR when deciding which one to use. SNR estimates based on jitter are convenient estimates for SNR across the entire Nyquist band. However, these may be too pessimistic for bandwidth-limited applications. SNR estimates based on an NSD measured at an offset frequency do not account for close-in phase noise, which could impact in-band measurements such as percent EVM. NSD is useful for out-of-band estimates such as noise-limited ACPR. Using the clock NSD curves and bandwidth-limited noise calculations along with the general equation for SNR would be the ideal solution for in-band and out-of-band estimates. Thank you for watching this presentation.